class we ended with we had derived this relation for a control volume. Now let us look at each of these terms and what they represent. So basically, if I try to draw a cartoon, there's a control volume V with a surface which is shown by the dotted line. So the left hand side dB by dt represents the rate of change of total quantity B of the particles present in the control volume at that time. So this capital dB by dt, or we also wrote this as small dB by dt. This represents, so if there are total particles which are there in the control volume, they have a property beta. We look at beta of each of these particles and add them up. So this is the property of those particles, and rate of change of properties of the particles which are present in the control volume is given by the left hand side dB by dt. Okay? Now the first term on the right hand side is partial by partial t of the volume integral of beta rho dV. This is the local rate of change of beta in the control volume added up for all the particles which are in the control volume. So this is the rate of change of beta which is there for the particles, and what will happen is you realize if the control volume is changing with time, then this term will not be 0. If the control volume is expanding or if it is contracting, then the volume integral, the volume itself is changing, so this term will not be 0. But in case if beta of the particles is not changing with time at one location, it may change from location to location, but at one location beta does not change, then such a flow we call a steady flow. Then partial beta by partial t will be 0. And if we choose a control volume which is fixed, then this term will always be 0. And I will discuss this more when we take up examples. So this is the local rate of change in beta. And the third term which we have, integral over the control surface this represents the net efflux or outflux of B from the control surface of the control volume. When I say net outflux or net efflux, it means if there is an inflow, then we add it up with a minus sign. Net rate of how much is the property flowing out of the control volume through the control surface, that is given by integral beta rho v dot n dA. Now, first thing we see is if the control volume has a surface such that Vs is equal to velocity of the surface. That means we are now if the velocity of the control surface is not 0, then the control volume is deforming, because it is either expanding or shrinking, or maybe expanding at some place, shrinking at some place. So, if Vs is the velocity of the surface, then what happens is, and let V sub r is equal to V minus Vs, that is the velocity relative to the surface. So, if the fluid is crossing out of the control volume with a velocity v, then V minus Vs is the relative velocity of the fluid with respect to the control volume. That means the control volume also has a speed, and the fluid crossing it has a speed which is different from the speed of the control volume. If it is the same, then the fluid will not cross. And the example again I gave is of the balloon which is expanding or deflating. If the control volume is leveling with the balloon, is matching with the balloon surface, then V will be equal to Vs. So, Vr will be 0. In this case, what happens is the equation, this stays the same, only this V gets replaced by Vr, because then it has to be relative to the control volume. So, therefore, in this case when we have this, so the flux term in Reynolds transport theorem has a Vr instead of V, and so the general form of Reynolds transport theorem is okay. So, this you can think of as the Reynolds transport theorem when the control volume is expanding or shrinking. Now, as far as this equation goes, this is valid for any control volume. The control volume may be fixed or it may be moving with respect to some frame of reference. Suppose if the control volume, if we have a situation where something is moving on wheels, we can choose a control volume which is fixed on the wheels. So, therefore, as the wheels move, the control volume also moves, and then this is still valid. So, whether the control volume is accelerating, non-accelerating, this is a very general relation. The only thing which we have is if the control volume is deforming, then the velocity here is the relative velocity with respect to the surface of the control volume when we calculate the surface integral. Now, notice when you calculate this integral and this integral has to be calculated for the entire volume. That means for the surface as well as inside. Whereas for this integral, we only have to go around the surface. Okay. So, now let us look at some remarks or certain things which will hold us. So the first remark we have is calculated for entire volume, that is the surface inside the CV, and the integral the second remark we have is, if we have a fixed or a non-deforming control volume, then let's look at this term d by dt. Now, since the volume is fixed, it is not a function of time. I can take the derivative inside. Okay, because V is fixed, it's not a function of time. So this I can calculate it. This I can say is equal to volume integral of but now here if the flow or the situation in the control volume is also steady. Steady means beta and rho will not change with time at a particular location. They can change from location to location, but at a particular location, which means the partial by partial t of beta multiplied by rho will be 0. So if the flow is also steady, then so this becomes sort of, in a lot of problems you will see which we solve, this case will be there. If you have, how do you say whether the flow is steady or not? If you have flow coming in, flow leaving, and if you just try to see if are things changing with time at a particular location. See, for example, if I have flow through an expanding tube, flow comes in, flow leaves. And if this situation is there at the start, initially there is air, I put in water, the flow is unsteady. But once the water fills the pipe, you have water coming in, water leaving, at each location, velocity is not changing with time. Whereas velocity is changing with x, because the flow is diverging or converging. But the flow will still be steady, then this term will be 0. And so using of Reynolds transport theorem in a lot of problems will become very easy. That basically you have to use dB by dt is equal to integral on the control surface beta rho v dot nd. Okay? So this becomes sort of a fairly easy proposition. Now the third thing which we have is, let's try to look at the integral over the control surface this term. So now here, if we have a situation like this, I have situation like this, flow is coming in a pipe, the area may or may not be the same, it could be converging, it could be diverging. It comes in with a velocity v1, it leaves with a velocity v2. Now here I have shown the control volume, I have in all the आज ऐसा करते हैं 6 बजे एक क्विज ले लेंगे, ठीक है ना? Today at 6 o'clock we'll have a quiz. But कोई बात नहीं, सिंपल सी होगी, so don't worry. You don't have to prepare anything for that. Okay. So we have flow in a pipe. What's the date today? ये मैं अभी बताने वाला नहीं था, बट जिस तरह से तुम लोगों का इंटरेस्ट क्लास में खत्म हो रहा था, I was forced to reveal it now. Otherwise, I would have revealed it only at 6 o'clock. So now, okay, let's come back. Okay, quiz नहीं हो रहा भैया, ठीक है, अब क्लास में ध्यान दो. So what we do is, in this control surface, we take the area, inlet part, we call it 1. The outlet part, we call it as 2. And the part which is touching the pipe, we have chosen a control volume which is only of the fluid. We call that circular part, the part which is touching the cylindrical portion, we call that as 3. Okay? So now, this is how you will be splitting up. Now what we realize is, 1 is inflow, 2 is outflow, and 3 is no flow. Now what can happen is, on 1 and 2, on surface 1 and surface 2, which is the area? Area is this vertical line. See, whenever you have to calculate V dot NDA, it has to be calculated for the line which you have drawn. So now, well, V could change with A or it could not change with A. So, for example, at this surface 1, if V1 is given in this form, that means it is 0 at the wall, it is some value and this distribution is given. So this is how V is changing with A. It could have some other form, it could be something like this, it could be a flatter one, or we could have, so here we could change with A, or we could have a case like this which I have shown. the velocity does not change with A. That means over the entire A1, velocity is constant. Now, such a situation, the second one which I have said, what we say is if beta if any property does not change with A, then we say this is a one-dimensional flow. That means velocity could change with x, but it is not changing with y. And not only velocity, any other property, if it changes only with x and does not change with y, then we say this is a one-dimensional flow. Okay? Now, what we do is now, if there is a one-D approximation, if we have a one-D approximation and if the velocity is v, then the cut which we make for the one control volume, we will make it perpendicular to the direction of velocity, if possible. In some cases it may not be possible, but if we make the cut perpendicular to the velocity, then what happens is v dot n will be either plus v or minus v. When will it be plus v? When will it be minus v? Same direction means inflow or outflow? Outflow. And minus v when there is inflow. So v dot n will be plus v if there is outflow and a 1D case, and minus v if there is inflow. And integral beta rho v dot nda will be equal to plus or minus beta rho times v times a at the boundary 1 or 2. So, v dot n will have one sign. It is negative if there is inflow, it is positive if there is outflow. Beta itself may have a sign. Beta may represent a component of velocity. So then this may also have a sign. So then there will be two signs. So eventually, for a one-dimensional situation, this whole integral just becomes beta rho va if velocity is perpendicular to the cut. Okay? So what I am trying to tell you here is simplifications. When you use the Reynolds transport theorem, how do you simplify things? Okay? So the volume integral we have seen, if it's a steady flow fixed control volume, the whole volume integral goes away. If it's a one-dimensional flow, then the surface integral just becomes beta rho va with a plus or a minus sign, which you work out accordingly. Because here, as I said, there could be two signs, one for v dot n and one for beta. So you take those two signs into consideration and then you can solve this. And the fourth observation which I have to make, so I am telling you about the Reynolds transport theorem, that Reynolds transport theorem is a general theorem valid for any control volume attached to any reference frame inertial or non-inertia. So, even if it is, if the control volume is attached to, is an accelerating control volume, there also Reynolds transport theorem per se will be valid. But then when you use the Reynolds transport theorem, the left hand side is dB by dt. Now, suppose if B is the linear momentum, then as you will say, see, we will put it as d of linear momentum by dt is equal to sum of external forces. But when I use this equation, that rate of change of linear momentum is equal to sum of external forces, then I will get a constraint. And the constraint will come from Newton's law, that Newton's law is valid only with respect to an inertial frame. So, the constraints will come from physics or the laws of physics, not from control volume. Reynolds transport theorem does not provide any constraints. Okay. So, now let us start using Reynolds transport theorem, and we will first use it for conservation of mass. And here we put beta is equal to 1, and so B will be equal to m. Now, this gives us this, you can think of as the Reynolds transport theorem applied for mass. Now, what is dm by dt? No, it is rate of change of particle, rate of change of mass of individual particles. See, because this is the left hand side is the property associated with particles. So, what is the rate of change of mass of any particle? It is 0. Mass is constant unless you are in the relativistic domain where you have E is equal to mc square working and energy can be converted to mass. But assuming we are not in the relativistic domain, then the left hand side dm by dt is equal to 0. In fact, this is such a basic law, we do not even call it a law of physics. Mass is constant is something which we always assume. So, this left hand side dm by dt so the mass balance for a control volume gives and if if we consider a fixed control volume, and but I say arbitrary. Arbitrary means it could be anywhere in space. If I have a big flow domain, it could be any region in space. Then this equation will become, so this will become 0 is equal to volume integral of and on the second term rho v dot n dA I can use as Gauss's theorem. So, this becomes divergence of rho v dV, and then what I get is I will get 0 is equal to volume integral of and now I make one more argument that since V is arbitrary, the integrand must be 0. That means this is valid for any V, not a particular V. It's a fixed V, but it could be anywhere in the control volume. So, and this is something like if I have a definite integral, integral a to b fx dx is equal to 0, then this does not imply that fx is 0. But if it is valid for any a and any b, then fx has to be 0. And another way of looking at this is you shrink the volume to a point. So, then this integral has to be, the quantity in the curly brackets has to be 0. So, therefore, what we have is, so this implies that and this is called the differential form of mass balance or the continuity equation, differential form of the continuity equation. This equation for a general volume, this is the integral form, and this, yes? No, this equation what we have derived, we did not use steady state anywhere.
So what if in a tank it is being filling or it is being empty but output is not equal to input? Then in this control volume.
So then yeah. So then within the control, we'll have a look at that. This is basically from the integral form I have got to the differential form of mass balance.
But dm by dt wouldn't be 0 in that case.
Which one? Partial m by partial t will not be 0. dm by dt will still be 0. Left hand side tells us, yeah, so what you will get is the rate of increase of mass in the control volume will be equal to whatever is the net efflux. See, dm by dt tells you the mass of individual particles. So, mass of, suppose if we have a control volume where water is being filled in a tank, as you said, and suppose let us say there is a small hole at the top that air is leaking out, and so water is filling in and air is getting leaked out. Okay? So, now here what is happening is, if you look at the overall density, then overall density is changing, But if I look at density of each particle of water or each particle of air, that is not changing.
What if the rate of flow of output is variable and input is also
So
input is also variable? So
it may be so, but then if that is so, then that will give you the net difference of the input influx and outflux will give you the amount of mass being accumulated in the control volume.
what if it is accumulating and diminishing?
It, so, so,
I'm just saying like it
so
wouldn't.
individual, see, individual particles only if the density is changing. If density of the particles is changing, then we will not have, that is what we call as compressible flow, where density changes. But individual mass of particles will not change, even if density changes. Mass of the particles will not change. So the left hand side represent the rate of change of mass of the particles.
You're saying rate of change of mass would be same. So in that case,
So whatever is the rate of change in the control volume is equal to the net efflux. So that is what the two terms in the right hand side tell you. Partial by, so when you have when you use the integral form, then you have to calculate these two terms, and the first term d by dt will not be 0. That would be a case of an unsteady flow where partial by partial t of rho dv will not be 0. And that will be equal to the net outflux plus whatever is going out minus whatever is coming in, all that will be equal to 0. I'll just take up some problems also of that type. Here what I've done is I've just written the differential form of the continuity equation or the mass balance equation. And the integral form is now we introduce another term called incompressible flow. In incompressible flow, density of the individual particles will not change, and a simple form of this is rho is equal to constant. Now in a flow, when we talk of rho is equal to constant, that is density is not changing. So this generally for liquids easy to maintain, or this situation in liquids the density when we talk of typical flows stays constant. But when we have flow of a gas, then its density could change, and the density will change either because of change with pressure or temperature. Because as we know, we take as two variables if it's an ideal gas. So pressure, rho would be a function of pressure or temperature. So in a gas it could change, and here I'm just giving you a rule of thumb. If If Mach number is less than 0.3, we treat the flow as incompressible. What is Mach number? V by C. V is the typical velocity in the flow, and C is the speed of sound in that medium. Okay? So, and actually the speed of sound comes because this is related to how density changes with pressure. C is equal to square root of dP by d rho. We are not doing compressible flows, otherwise I would have derived that relation in the class. But here you will have to take this for granted, that you look at the flow speed, typical flow speed, divide that by speed of sound in that medium, and if this is less than 0.3, you can assume the flow is incompressible. That is, the density is not changing. स्पीड ऑफ साउंड आता है इनमें क्योंकि स्क्वायर रूट ऑफ dp by d rho, pressure by density, that is equal to c, the speed of sound. So how the density changes when there is with changes in pressure. So that is how this comes in, and I would have done this if we were doing some lectures on incompressible flows, on compressible flows. Sorry. So here I am just giving you this as a guideline. So for at least in this course we will treat all flows as incompressible. That is, density is not changing. So now for an incompressible flow now, so we will assume rho is equal to constant. So now our equation is d by dt integral so if the control volume consists only of one fluid, and if this is, so we can pull now rho could be pulled out of the integral. So this becomes rho times so, and now if volume is fixed, and if we have and in addition, if the flow is one dimensional, then at each of the inlet and outlet, this term will become Vi times Ai, and it will have a plus sign if it is an outlet, minus sign if it is an inlet. So this term will just become this, and so this is, and plus for outlet, minus for inlet, and this we can say is equal to plus minus Q sub I. We had done this. Flow rate is equal to V dot NDA. So that becomes equal to the sum of all the flow rates is equal to 0. And in particular, if there is one inlet and one outlet, then we get, let's say the inlet is 1 and outlet is 2, minus V1A1 plus V2A2 is equal to 0, and this becomes V1A1 is equal to V2A2. So this equation you may have seen, this is called the continuity equation. V1A1 is equal to V2A2, and it directly follows from mass flow. But you see how many approximations are needed to get to this form. So it's not that it's such straightforward. So this is what is called as the continuity equation. Now if flow changes with the area, then Q dot is equal to integral V dot NDA, and one can define V average or V bar is equal to Q dot upon A. So sometimes we talk in terms of an average velocity, but this, if the flow is uniform, then the average velocity is equal to V1 or V2. Otherwise, you calculate the total flow rate, divide that by the area, that will give you an average velocity. Because a lot of things are done in terms of average velocity, so I thought we will introduce this here. Now there is a special case of mass conservation where we take beta is equal to 1 over rho or specific volume. So B is equal to so now Reynolds transport theorem becomes dV by dt Now this looks a bit confusing. What is the left hand side represent? What does the left hand side here represent? The rate of change of volume of all the particles which are in the control volume. Whereas the first term on the right hand side is the control volume, whether it is changing with time or not. Okay? Now, if density is constant, then what happens to the volume of the particles? It is same. So therefore, it will not change. So if density is constant, then the left hand side is 0. The right hand side, the first term is 0 if the volume is constant. Okay? So now there could be two cases, as he was talking of a case. Suppose if I talk of let's take of a Again, there could be two cases in the same thing. One, we could talk of that the air is getting pressed. There is no leakage at the top. And the other case could be there is a small vent at the top from where the air could leak out. Okay. Now, let's try to think about this. When this is happening and now I choose a control volume. I have to choose a control volume. I choose a control volume. Let's say I've chosen this. This is incompressible as far as each particle goes. Okay. Now I've chosen a control volume which is the dotted line. Now in this control volume, as the water fills up, this level will change. Okay. Now, again, I could probably have chosen two control volumes within this, one consisting only of water and the other consisting only of air. Okay. So, now you have to think about this, in which case, when I look at the left hand side, dV by dt, this tells me the rate of change of volume of particles. Now, if I look at the density, if I look at the density of water does not change. But what about the density of air? It will change. It will change. So, therefore, what will happen is dV by dt for this entire control volume, the left hand side, is not equal to 0. Because in the control volume, the density is changing. So, if the density is changing, then the volume of particles is also changing. So, the left hand side is not 0. And in particular, if I choose a control volume consisting only of air, then it is very clear that the density of the air particles is changing. So, therefore, the left hand term is not 0. The reason I have taken the entire control volume is, if I look at the total control volume, in this control volume, the total volume does not change. Okay? So, therefore, partial V by partial T is 0. dV by dt is not 0. And this will be equal to, this dV by dt will be given by integral V dot n dA. Now, what is V dot n dA? For this entire control volume, there is, let's say, this area is A1, the velocity is V1. So, this term is only minus V1A1. Okay? So, when I use the volume continuity equation on the entire control volume, what I get is dV by dt is equal to minus V1A1. Okay? That may not help me give any quantity. But this is just to explain the difference between partial V by partial T and dV by dt. Partial V by partial T in this case is 0.
Its mass will be constant. It's very small, so its volume would also be constant. Here, the left-hand term which we are talking about is the number of particles is increasing in the control volume.
No, left-hand term, no, not number of particles. Not because of that alone. Because the density of the air is changing.
But sir, अगर हम माइक्रो लेवल पे देखें पार्टिकल तो बहुत
नहीं, तो इसमें अभी हम ऐसा कर सकते हैं ना, इसको दो पार्ट्स में बांट दें, एक वाटर वाले पार्ट में, एक एयर वाले पार्ट में. अगर वाटर वाले पार्ट में हम बांटते हैं, so then what we will, and let's consider a second control volume which consists only of water. So then what I have is, for that control volume dV by dt is 0, water density is not changing. partial V by partial T will be equal to dH by dt times the area of that base. Okay, and V dot NdA will be equal to A1 minus rho 1 V1 A1. So from there what you will get is, what is this dH by dt? And if I apply it only for the air, then if my control volume consists only of the air packet, then what is happening is partial V by partial T is not 0, because it is equal to minus dH by dt times this. dV by dt is also not 0 because density is changing. But in this control volume, which consists only of air, there is no entry and there is no exit. So this term becomes 0. And so you can get what is dV by dt of this control volume.
सर मतलब हम ये बोल रहे हैं कि इतने छोटे पार्टिकल्स भी डेंसिटी चेंज की वजह से उनका वॉल्यूम चेंज हो रहा है.
मतलब एयर वालों का तो हो रहा है ना, वाटर का नहीं हो रहा है. बट एयर की क्योंकि डेंसिटी चेंज हो रही है तो इसलिए. बट सी दिस टेल्स यू दैट इन सम ऑफ द प्रॉब्लम्स वेयर particles don't change. I'll take an example in the next class. Today I will leave you here only. But in the next class I'll take an example where we'll use this sort of a continuity equation where individual particles don't change their volume at all. So therefore dm by dt is 0. And there also if the control volume is fixed, this will also be 0. So then you will have minus V1 A1 plus V2 A2 will be equal to 0. So there, even if there are different things which are coming in, for example, if a piston is being pushed, it has a velocity V1 and it is causing some fluid to go out, then V1 A1 of the piston will be equal to V2 A2 of the fluid. So that is what we'll take an example. Now, so in this case, the one which I have shown consists of both air and water. So now, okay, let me write this, okay. So we could also have this control volume divided into two parts. Let me complete this. A of water, B of air. Note these CVs, in these CVs, partial V by partial T is not equal to 0. So, for example, let's consider water. So, we have this tank coming like this. CV consisting of water. Only of water. So let's say this is H, this is AT. So here dV by dt is equal to 0. Partial V by partial T is equal to AT times dH by dt, and integral over the control surface rho V dot NdA will be equal to rho of water times this is V1, this is A1. So now mass balance would give me 0 is equal to rho of water AT dH by dt minus rho W V1 A1 is equal to 0, and this would give me dH by dt is equal to V1 A1 by AT. This is something which you would have expected. Another way of getting the same result is, you say you have a control volume which at this instant is fixed with the top surface. So there the water is leaving, but it is leaving with a velocity V2. And V2 A2 will be equal to V1 A1. And V2 is nothing but dH by dt. So you could have conceptually done the problem even doing a fixed control volume, where you say the fixed control volume is at that instant, only at the top. So the velocity there is V2. And V2A2 is equal to V1A1, and you get the same result. So this is for control volume consisting only of water. And now if I look at CV, if I look at air, and let density is equal to rho air, which is a function of time. So now here what we will have is dV by dt So in this control volume, partial V by partial T will be equal to and what we get is dV by dt is equal to and this volume then we can relate. That is what this volume is basically. If you say mass of the air is constant, so this will be equal to mass divided by the density. So then you can get the density from here, how density is changing with time. Okay. ठीक है, तो we have seen this example how to, but sometimes this volume continuity equation is also very useful, particularly in cases where density is not changing with time in the entire control volume. Here density was changing with time. But suppose if there was a hole at the top, then density would not have changed, and then you would have got V2A2, V1A1 is equal to V2A2. Okay, thank you.